He spent the last 5 years working at the University of Namibia as the local project scientist for the Africa Millimetre Telescope project. And the ASB is very glad and pleased to introduce Rhodri to you. Rhodri, over to you.
Okay, thank you for that introduction. So I'm going to turn my video off and start the screen sharing. And hopefully I can find my presentation. There it is. Okay, so let me go into, oops, before I do that, let me just hide names of annotators. There we go. Okay, let me go into that. So the title of my talk this evening is Seeing a Black Hole with the Africa Millimetre Telescope. And as was said in the introduction, I've just joined the staff at BIOS, but up until the end of June this year, I was at the University of Namibia, where I spent 5 years working on this project. So let me give a summary of what I'm going to talk about. I'm going to start off explaining what a black hole is, talk about the black hole at the center of our Milky Way galaxy, the evidence for it, and then talk about something called the Event Horizon Telescope. And the Africa Millimetre Telescope will form part of the Event Horizon Telescope. I'm going to talk about where the telescope will be put on somewhere called Mount Gamsberg in Namibia, talk about the telescope a bit, and then the construction and first light of the telescope. So that's the plan. So as I just said, I've recently arrived in Palapi. So on the 28th of June, I took the long trip in my car all the way from Windhoek to Palapi, 2 days for me of driving. Thankfully, I arrived safely in Palapi on the 29th of June. So I've been here nearly exactly 2 months at BIOS. Okay, let me just clear that annotation. So even though I've recently arrived at BIOS, because the work I'm talking about here is related to my time at the University of Namibia, I've kept the slides, the background, if you like, of the slides as University of Namibia. Hopefully, and this is something I can maybe talk a little bit more at the end, I'm hoping BIOS can become involved in the Africa Millimetre Telescope project, but at the moment, as things stand, it doesn't have any formal involvement. So let me start off by talking about what a black hole is. A lot of people mistakenly say that black holes really weren't thought of until Einstein's theory of gravity, the general theory of relativity, or some other people say that they really weren't thought about until the early 60s, and that's not correct. The first person to propose the idea of a black hole was John Michell, who was actually not even a physicist or an astronomer, he was a geologist. But he proposed the idea back in 1783-84, this idea that you could have an object from which light couldn't escape. And of course, this was long before anyone knew of the details of light being the fastest that anything can travel. So it turns out that every object has an escape velocity. The saying, what goes up must come down, is not true. If you could throw something quickly enough up into the air, 11 kilometers per second, it would not come back down. Now, obviously, no human being can throw that fast. But of course, this is what rockets do, essentially. When they escape the Earth's gravity, they don't have to go at 11 kilometers per second all the way, because as you get further from the Earth, the gravity gets weaker. But every object has an escape velocity. For the Earth, it's about 11 kilometers per second. It actually depends on exactly where you are. It's less by the equator because the rotation of the Earth helps you. For a neutron star, which I'm sure most of you know is one of the end products of the death of a massive star, a neutron star typically has the mass of maybe 3 times the mass of the sun, but squeezed down into something maybe 10 or 15 kilometers in diameter. So an incredibly dense object, basically comprised entirely of neutrons, no space between any of the neutrons, unlike normal atomic matter, which is 99.99% empty space. If you were to calculate the escape velocity from a neutron star, it turns out it's about 80% the speed of light. So I'm using the symbol c to represent the speed of light. That's the symbol physicists use. So about 80% of the speed of light is the escape velocity from a neutron star. How do we actually calculate the escape velocity of an object? I'm not going to go into all the details, but it's a fairly simple calculation. You can get an idea of the escape velocity using classical mechanics. Now, to understand the details of what goes on in the extreme gravity of a black hole, you actually have to use Einstein's theory of gravity. But to get an idea of what the escape velocity would be from an object, be it a neutron star or the Earth, you can do a reasonably get a reasonably accurate value just using a very simple calculation using classical Newtonian mechanics. And if you go through the steps of doing that, you find that the escape velocity is given by this very simple formula that I've got up the top here. So it is, let me change the color of that so you can see my annotation a bit better. So it's the square root of 2 times the universal gravitational constant, big G, which essentially determines the strength of gravity, multiplied by the mass of the object you're trying to escape from, divided by its radius. So that, if you think about it, if you can squeeze the same amount of mass into a smaller volume, for example, if you squeeze the Earth down to a smaller size, then the escape velocity would go up. And then by definition, you have a black hole when the escape velocity becomes greater than the speed of light. So that's what we mean by a black hole. It's an object whose escape velocity is so great that not even light can escape from it. And the point at which the escape velocity is equal to the speed of light, we call that the event horizon. And I can explain maybe at the end of the talk where that term comes from. Now, in 1916, the same year that Einstein published his theory, Karl Schwarzschild worked out the solution to his equations of general relativity for a non-rotating black hole. So another term that's used for the event horizon is the Schwarzschild radius. They essentially mean the same thing as long as the black hole is not rotating. If the black hole is rotating, the solutions are different, and you have something called the Kerr radius, K-E-R-R, but Schwarzschild was the first to work out the solution for a non-rotating object, work out the size of the event horizon for a non-rotating black hole using Einstein's equations. So this is, as you can see, way back at the beginning of the century, but really there wasn't much interest in black holes from Einstein publishing his theory until the early 1960s. And one of the most famous physicists of the last 100 years, Stephen Hawking, and other people in the early 60s reignited interest in black holes because they studied the theory of them. But from the observational point of view, there was also work being done. So in 1964, an American astronomer, Edwin Salpeter, he suggested that the huge amount of energy coming from the centers of some galaxies could be due to supermassive black holes. So he was the first person to suggest that possibility. And here's a copy of the abstract of his paper. And if you look down towards the bottom, you can see that it's dated 1964. Let me again just highlight that. So he was the first person to suggest that maybe the large amount of energy coming from the centers of some galaxies could be due to a black hole. And then nothing really much happened from the observational point of view until the early 1970s, or sorry, I should say from the theoretical point of view, until a series of papers by Martin Rees and co-workers built on this idea that Salpeter had suggested. Now, some of you may have heard of Martin Rees. He's the current Astronomer Royal. The British Astronomer Royal has been for, gosh, probably over 20 years by now. He was also president of the Royal Society at some point in the last 10, 15 years. One of the most productive and famous theoretical physicists. And he wrote a series of papers in the early 1970s suggesting that indeed the large amount of energy coming from the centers of some galaxies could be due to a black hole. Here's a paper he wrote with Donald Lyndon Bell in 1971. So the title on quasars, dust, and the galactic center. Some of you may know that quasars are these mysterious objects which we now understand, which look like stars, but when you measure their redshift, they are moving away very, very quickly. So it was realized quite early on after their discovery that they must be the very bright, well, they must be very far away to be moving so quickly. They cannot actually be stars within our galaxy. We now understand they are the active centers of galaxies. So Martin Rees was suggesting that black holes could be associated with the intense output from quasars. And I've highlighted a section here. If we regard quasars as hyperactive galactic nuclei, then a black hole might lurk in the centers of most normal galaxies. Now, this is an incredible statement to make in 1974. This was in the Observatory magazine, which is the magazine of the Royal Astronomical Society. So essentially a magazine aimed at amateurs as much as professional astronomers. But he suggested that there could be, as you can, if you reread what I've highlighted there, he suggested that there could be a black hole at the center of most normal galaxies, not just the ones with a prodigious amount of energy coming from the centers, but most galaxies. It turns out that he was right, because the Hubble Space Telescope discovered about 15 years ago that indeed every galaxy we look at appears to have a supermassive black hole at the center. So Martin Rees had predicted it 40 years in advance, or at least suggested it. So in 1974, Martin Rees proposed, as I just said, that active galactic nuclei may harbor supermassive black holes. In fact, he suggested, or even normal galaxies. And in the same year, 1974, there was a breakthrough from the observational point of view. A compact radio source, which we now call Sagittarius A star, was discovered by Ballack and Brown using the Very Large Array of radio telescopes in New Mexico. Now, I'm sure all of you know that the galactic center is in the constellation Sagittarius. So after the discovery of this compact radio source, once it became understood as to what it is, we now know that this is essentially the center of our Milky Way galaxy. So this is the paper in which they published that. As you can see, 1974, if you look at the date here, received on June the 3rd, 1974. And this is the picture that they showed, or rather a contour map. Now, if you look back at radio astronomy papers, it was far more common, I would say, up until the last 10 or 15 years, to display the information using contour maps rather than actual images. That seems to have changed in the last 10 or 15 years. Now, people are far more comfortable with false color images, so the information would be displayed as an image with false colors. But you can see the compact source. The elongation that you see is probably not real, because this is the beam of the telescope. So as you can see, it has an elliptical beam, and that's just because of the way that the array used to get this image works. So that is the discovery image, and it was discovered at a frequency of 8,085 megahertz, which, if you prefer to think in terms of wavelengths, that's 3.7 centimeters, so in the radio part of the spectrum. Now, of course, since this discovery, it's become one of the most observed objects in the sky. So I'm going to show you a couple of examples. This is an image taken with the Spire camera on the Herschel Space Observatory. So the Herschel Space Observatory was, until recently, the largest telescope ever put into space. It had a 3.5 meter diameter mirror. It's, of course, now been surpassed in size by the James Webb Space Telescope. But these images were taken by Herschel. and the Spire camera on Herschel at far infrared wavelengths. So you can see the wavelengths at the bottom there. 250 is the left-hand panel, 350 and 500 microns. You cannot see the center of the Milky Way galaxy at visible wavelengths because of all the dust. Again, I'm sure most of you know about the dust that causes the dark patches that we see in the Milky Way. So that obscures our view of the center of the Milky Way at visible wavelengths. But when we go to longer wavelengths, or actually even shorter wavelengths, we can see the center of the Milky Way. So these are longer wavelengths in the far infrared. And then this image is a combination image. The red in the image is infrared, not far infrared like in the previous image, but more mid-infrared. And then the blue is actually X-ray emission. And you can see the blow up of the very central part here, showing the intense X-ray emission, which is coming from the center of Milky Way galaxy. Now that is telling us that there's very hot gas. You get thermal X-ray emission from very, very hot gas at millions of Kelvin. So that's what's producing that X-ray emission. Now, it turns out that there have been teams studying the motions of stars near the center of the Milky Way galaxy since the since the late 1980s. So a team at the University of California, Los Angeles, and then another team at the wonderfully named Max Planck Institute for Extraterrestrial Physics in Germany. They have been studying stars in motion around the center of our galaxy, and have built up by now a nearly 40-year history of the motion of those stars. So they have published, of course, dozens and dozens of papers over that time. I'm just going to show you one from each of the teams. So this is from the Max Planck team in Germany and Reinhard Genzel. I will highlight his name here. He's the head of the team. And in fact, a couple of years ago, he shared the Nobel Prize for this work. So in this paper, they mention, they use the motion of the stars, and I'm going to show an animation of this in a minute or two. They use the motion of the stars to then determine the mass of the object about which the stars are rotating. So that's the German, or the team based in Germany. And then another paper by the team at UCLA, and the lead author on this is the head of that team. And she also shared in the Nobel Prize, Professor Gez. I'm probably mispronouncing her name, so I apologize. So that team is based at UCLA. Now, obviously, you can't read these abstracts in the time that I'm showing them, but if I just go back to the previous one, the German team, and highlight the mass that they calculate, which is mentioned in the abstract. So it is here. 4.31 times 10 to the 6 solar masses. So in other words, 4.31 million solar masses is the mass that the Max Planck team calculate for the object at the center of our galaxy about which these stars are orbiting. And the UCLA team calculates a mass of 4.5. So within the errors, you can go back and look at the errors, they agree. And they also, the important thing is they also determine the extent of the massive object about which these stars are orbiting, and the size of the object about which they're orbiting is far too small to be explained by anything else except a black hole. So they can't be just orbiting a mass of gas or of stars, because the object about which they're orbiting is far too compact. It has to be, at least in the physics that we understand, it has to be a black hole. So there's now overwhelming evidence that there is a central black hole, supermassive black hole at the center of our Milky Way galaxy with a mass of, as you saw from those two abstracts, just over 4 million times the mass of the sun. I'm now going to show an animation which has been done. This is from the UCLA team. So when I press play, you're going to see, there we go. Now, these are actual observations of the dozens of stars that they've been observing for the last nearly 40 years. going around the center of our Milky Way galaxy. Just over 30 years they've been observing them. Some of them have come close to completing orbits. And so from studying the size of these orbits and the speed of the orbits, you can actually determine the mass of the central object about which they're orbiting. And that's how this work has been done. So if you have a black hole, remember the equation for a black hole, the size of the event horizon basically depends on the mass of the object. That's the only thing it depends on. So if you know that the mass is about 4 million times the mass of the sun, you can work out the size of the event horizon for the black hole. And if you do that, you find that the size of the event horizon for such a black hole with a mass of just over 4 million times the mass of the sun is 1.18 times 10 to the 10 meters, which is what, about nearly 12 billion meters. Sounds huge. But then, of course, you've got to remember that the center of the Milky Way is a long way away. So we are about 8,000 parsecs, 8 kiloparsecs from the center of the Milky Way galaxy. So that means that the event horizon subtends an angle in the sky of just under 10 millionths of an arc second, 9.9 micro arc seconds, 10 millionths of an arc second. Now, if you're an observational astronomer, you know that you're happy if you get a seeing of about 1 arc second. And from the very best observatories in the world on high mountains, we sometimes can get a seeing, a resolution of about half an arc second. We are talking of trying to see an object which is only 1/10 millionth of an arc second across, an incredibly small angle. The resolution of a telescope theoretically is given by a very simple formula that the theta expressed in radians is just 1.22 times the wavelength divided by the diameter of your collector, the telescope, if you like. And so you can work out what size telescope you would need at different wavelengths to see such a small angle. And at visible wavelengths, you would need a telescope 3.5 kilometers across to be able to resolve an angle of 10 millionths of an arc second. Now, obviously, you cannot build a telescope, at least here on Earth, 3.5 kilometers across. So doing it at visible wavelengths is not possible. If you were to go into the radio part of the spectrum, and the most popular, I think I can say the most popular wavelength in wavelength astronomy is the 21 centimeter line of neutral hydrogen. It was the theoretical prediction of this 21 centimeter line for neutral hydrogen that kind of led to the birth of radio astronomy, or at least its growth in the 1950s and 60s. So if you work out what diameter telescope you would need at radio wavelengths, you get a diameter of just over 1.25 million kilometers. Now, it turns out that astronomers have developed techniques in the last 40, 50 years to link telescopes together using a technique called interferometry. So the VLA, the Very Large Array that discovered Sagittarius A star, is indeed an array of telescopes in New Mexico. And in fact, we can link up telescopes in different parts of the world and then use this technique to effectively have a telescope that is as large as the separation between the two telescopes. Now, at visible wavelengths, as far as I'm aware, the longest baseline that we've been able to use to do interferometry is at the Very Large Telescope in Chile, the ESO VLT. And the 4 telescopes there are only a couple of 100 meters apart, and they have been able to do interferometry over that limited distance. The reason we can't do it over larger distances at visible wavelengths, there's a couple of reasons, and I'm happy to explain that towards the end. We can do it very easily at 21 centimeters, but in order to have a telescope, two radio dishes separated by 1.3 million kilometers, the one dish would, for example, need to be on Earth, and the second dish would have to be about 3 times further away than the moon. And although in the future that could well be possible, we don't have such radio dishes out in space at the moment. if you come to a wavelength, which I'm going to call the sweet spot, 1 millimeter, you need a diameter of 6,350 kilometers. So it turns out that 1 millimeter is a sweet spot because it's long enough that we can do interferometry over large distances, which we cannot do at visible wavelengths, but it's short enough that the Earth is actually big enough to give us these baselines. If you know the radius of the Earth, you know that that is about the radius of the Earth. So that's telling you that you don't need millimeter. If you do this at millimeter wavelengths, you don't need one of the dishes to be in space. It can just actually be on a different part of the Earth. The Earth is big enough to give us these kind of baselines. So with our current technology, millimeter wavelengths are actually currently the only way to image such a small angular size. So that is why the effort has gone in to developing a network of millimeter wave telescopes to do exactly that. So some of you may know, if you've been following the astronomy news in the last couple of years, that this was done in a couple of years ago now, 2019, I think it was April of 2019. I'd have to check the dates, but these images came out in 2019. The black hole at the center of Messier 87, or at least the event horizon of the black hole at the center of Messier 87 was released. The images themselves were taken in 2017, and then it took a couple of years to analyze the images, and they were released in 2019. And on the left-hand side of the panel of images here, you can see the angular size. So this is 50 millionths of an arc second is that line. So you can see that the event horizon of this telescope is about 50 millionths of an arc second, far too small to be able to see with any other technique that we have available at the moment. And the four images show the slightly change in appearance of the material around the black hole over the dates shown. Now this, when this news broke in 2019, it made the front page of nearly every newspaper, well, I shouldn't say nearly every newspaper in the world, hundreds of newspapers. So this is an array of the front page of some newspapers that the European Space Agency put together. And I would imagine most of you heard this story because it was such big news. So this was a few years ago, but then just a couple of months ago, the same team released the first ever image of our own galaxy's black hole. So this was released. You can see the date on this article if you look close, if you know where to look. The date is up there. So this is the front page of the Independent newspaper in Britain. So these images were released on, well, they were released on the Thursday, the 12th of May, and the newspapers carried them the following day. So that's the front page of the British Independent newspaper. This is the front page of the article from the Guardian newspaper, and here's the New York Times. So again, this story made the front page of many newspapers. And these images were taken with something called the Event Horizon Telescope. So let me now show you what that network of telescopes looks like. So all of the, I guess, these are all telescopes within the network. I was trying to think of a term to use there. So all of these points in this map are telescopes within the Event Horizon Telescope network. And as you can see, there are a couple in Europe, a couple in the United States, including way over in Hawaii, which is, I'll come back to that, and a couple in, one in Mexico, the Large Millimeter Telescope in Mexico, and a couple in Chile. So for example, the Atacama Large Millimeter Array and Apex in Chile, in the high charged Ñancho Plateau of the desert in Chile. And there's even one at the South Pole. And I think, I don't know if I have a diagram of this, but this diagram doesn't show it, but there has recently been a telescope in Greenland added to this network. But as you can see, there's absolutely nothing in our part of the world. So the idea is to build a telescope here in Southern Africa. And as I will explain, the best place for this telescope is Namibia because of the extremely dry conditions there. So I'm now going to show you a little animation of the linking up of all of these different telescopes. So basically, you point all of these telescopes, or at least as many of them as you can in the network, simultaneously at the object you're trying to observe, and then they take data at the same time. And the animation I'm about to show illustrates the sort of baseline between the different telescopes, because it all comes down to how large the baseline is. The larger the baseline, the better the resolution, because it's a larger separation between the telescopes. So this animation, let me start it, will show various telescopes linking up, and the blue dot, which is at the moment way over on the left there, represents the Africa Millimetre Telescope, which is yet to be built. So all of the red lines that you see linking up are telescopes that already exist in the network, but the sort of blue lines or turquoise lines linking up are baselines which include the AMT. So let me play that, and you can see these different baselines linking up. And in the bottom right-hand corner of the diagram is something called the UV plane. So when you do interferometry, you actually work in Fourier space, and the UV plane is represented down in the bottom right there. And the blue curves that you can see in the bottom right are basically telling you that you get a better coverage in the UV plane. And that allows you to fill in. So although having two telescopes separated by a long way will give you very high resolution, what it won't give you is information on a large scale. So actually you want a variety of different baselines, and this is what most interferometers do. The VLA in New Mexico uses long and short baselines. The long baselines give you the high resolution, and the shorter baselines give you the more wide field information. And that's basically referred to as coverage in the UV plane. So the better the coverage, the more complete the coverage in the UV plane, the better you can create the images, synthesize the data. Now, an important point about the AMT, which is one of the reasons that we would want to put it in Namibia and not, for example, further to the east in Southern Africa, is there is a brief moment of maybe no more than half an hour, but still half an hour is better than nothing. When you get the entire diameter of the Earth, you can get the AMT linking up with the telescopes in Hawaii and using a baseline of about 13,000 kilometers, which is obviously the longest that you can get on Earth. So that is one of the reasons why putting the telescope in Namibia has advantages. So it turns out that the AMT, the Africa Millimetre Telescope, will enhance the Event Horizon Telescope's angular resolution, and it will improve this UV coverage that I was talking about for both the central black hole of Messier 87 and our own central black hole. And this picture here quite nicely shows that. So on the left-hand side, we have an artificial input image. This is just created on the computer. And then on the right-hand side, we have how that image would look using different combinations of arrays. If you were to have the full array including the Africa Millimetre Telescope, you get an image that looks like that. If you remove the Africa Millimetre Telescope, or if it existed and you removed it, you can see the degradation in the image. It's actually greater than if you remove ALMA. And the reason for that is, even though ALMA has many dishes, this is not a problem relating to sensitivity. It's a problem relating to getting resolution. And because the AMT is further away from most of the telescopes in the array than ALMA is, you actually get more of an improvement in resolution by including the AMT than you do by including ALMA. If you remove both from the array, then you can see the image degrades quite a bit. Now, because of course the AMT will be in the southern hemisphere, and most of the telescopes in the network, apart from a few, are in the northern hemisphere. It'll obviously improve the ability to observe objects in the southern hemisphere. So that's also important. Before I move on to the next slide, one thing I should point out, I'm just going to go back to the slide that illustrates the positions of the telescopes in the array. Most of these telescopes are have not been, in fact, all of them have not been built to be part of the Event Horizon telescope. They are already existing telescopes, which this consortium, the Event Horizon Telescope, tries to get time on. And ALMA, for example, is one of the most sought after observatories in the world. So it can be a problem to get time on these highly oversubscribed millimeter wave dishes to actually do this work, even though it's important work. So another illustration of the problems with having telescopes in different countries, which you may not have thought about, is the LMT in Mexico became inaccessible for about a year and a half because it was too dangerous to drive to the telescope because of some feuds going on between rival drug gangs. So even though the telescope was there, the people working on the telescope couldn't actually drive to and from work. It was too dangerous. So the AMT will actually be built with this project in mind. It'll be dedicated to this project. So when the network is observing either the galactic center or Messier 87 or some other object to try and some other galaxy to try and see the central supermassive black hole, the AMT will not be busy doing something else because it'll be dedicated to this project. And that's an important point. Okay, let's go through these slides. So most of the times I've given this talk, it's been to astronomy societies in the UK, and of course they don't know too much about Namibia. I'm not sure how much Botswanans know about your next door neighbor, but let me say a few things about Namibia. It's more than 3 times the size of the United Kingdom, so about 820 million kilometers squared. Botswana, I don't know the area of Botswana, but looking at a map, it looks smaller, but they both, of course, have similar small populations. So the population of Namibia is only just over 2 million. It's the second lowest population density in the world. Now, when I give this talk to astronomical societies in Britain, I point out that the UK, which is less than a third the size of Namibia, has a population of 65 million. So obviously you can see the huge difference in population density between a country like Namibia, or Botswana for that matter, and most northern hemisphere countries. So a low population density is obviously very, very useful in astronomy. And it has the driest climate. Namibia has the driest climate in sub-Saharan Africa. And I would imagine the climate in the western part of Botswana is equally as dry. But obviously, when you start including the eastern part of Botswana, it's not quite as dry. But Namibia is drier as a country than Botswana. And that's important, as I will come back to in a minute. And the Tropic of Capricorn passes within about 100 kilometers of Windhoek, and I think a similar distance to Palapi. And if you've tried to observe the center of the Milky Way galaxy, you know that here in Botswana and in Namibia, it passes high overhead, which is not the case if you're in the northern hemisphere. It's always low in the sky, even when it reaches its highest point in the sky. And much of Namibia is actually high plateau. So Windhoek itself is at 1,700 meters. So I looked at Palapi is just under 1,000 meters altitude. And most of Namibia is high plateau. And I will mention the altitude of where we're going to put the telescope, because that is also important. And just like Botswana, it has a huge number of clear nights a year. I joke about this when I talk to UK-based astronomy societies, because I think British British amateur astronomers are lucky if they get 60 clear nights a year. And I joke that they would be totally exhausted if they lived in a country like Namibia or Botswana, where they could be up so many nights a year getting observations. So the telescope itself is going to be put on a mountain in Namibia called Mount Gamsberg, or Gamsberg if you use the Afrikaans pronunciation. And the location of Mount Gamsberg is... Yeah. It's southwest of Windhoek, about 200 kilometers, I would say, west-southwest, or possibly southwest. So it's in a drier part of Namibia than Windhoek. I lived in Windhoek for 5 years, and it's pretty dry, but the location of Mount Gamsberg is even drier. And there is already a major international observatory very near where we're going to put this telescope. So this is a picture of HESS, which is an array of telescopes that observe the flashes produced when gamma rays from space strike the upper atmosphere of the Earth. And in the background here, let me illustrate it, is Mount Gamsberg. I'm going to show some other pictures of Mount Gamsberg in a minute, but this is Mount Gamsberg in the background. It's about 30 kilometers as the crow flies from HESS. Let me show you a closer picture so you can see it's got a nice flat top to it, a little bit like a mini Table Mountain. And this is a picture showing the precarious route up to the top of the mountain. Now, in August of 2019, I went up that road, and I must say, I thought I was going to die every hairpin bend we went around, because the four-wheel drive truck we were in, as it turned each of the hairpin bends, at least one of the wheels would be entirely off the road because the bends are so tight. So what about preliminary testing of this site? Well, it turns out that extensive site testing has already been done. So the European, let me just go back to the previous slide. The European Southern Observatory did extensive site testing of Mount Gamsberg in 94, 95 for an entire year, from the middle of 94 to the middle of 95. And the reason they did that is they were considering the site as the location for the Very Large Telescope, which was subsequently built in Chile, but they were considering Gamsberg, mainly because of the political situation in Chile. And so these are some illustrations of the measurements they took of the amount of water vapor that is in the atmosphere above Mount Gamsberg at different times of the year. And without going into the details of all of these plots, what they basically show is that particularly in the dry time of the year, which is the same as the dry time of the year here in the June, July, August, September period of the year, Mount Gamsberg is extremely dry and certainly ideal for doing millimetre-wave astronomy, because water absorbs millimetre wavelengths. Now, even in March, and the reason I mentioned March is because each time the Event Horizon Telescope has done an observing campaign, it has done the observing campaign in March, because that is when it is driest for most of the telescopes in the network. Remember, the network of telescopes has a number in the most of the dishes are in the northern hemisphere, and so the driest time of the year for most of the telescopes in the network is March. Now, even though March is not the best time of the year for us here in Southern Africa, still the transmission is good enough to do this kind of work. Remember, I mentioned earlier, we don't really have a problem with the strength of the source that we're trying to observe. It's the resolution that we want to really improve. So certainly the transmission of the atmosphere in March, although it's not as good as July or August, it's good enough to do this work. Now, we had a master's student at the University of Namibia who worked, he finished his master's in 2019 under my supervision, and he used 8 years worth of data taken by an infrared camera at HESS to infer the precipitable water vapor over those 8 years at Mount Gamsberg. so not a direct measurement, but an inference of what the precipitable water vapor is at Mount Gamsberg over those 8 years. And UNAM, the University of Namibia, has borrowed a geostation from the Hartrau Observatory in South Africa. And this will be put on top of the mountain. It's currently at Hess being tested. It will sit on top of Mount Gamsberg and measure precipitable water vapor indirectly using GPS. And if someone wants me to explain how GPS can be used to measure water vapor, I can do so at the end. And we are working with a team at the University of Pretoria that are developing a low-cost radiometer. So a radiometer is the only direct way to measure precipitable water vapor. That's what ESO did when they did the site testing in the mid-90s. Usually, radiometers cost about $100,000 but the University of Pretoria is developing a low-cost radiometer, which will cost about $5,000, and that is cheap enough that we can buy one for this project. Let me say a little bit about the telescope. So we are not going to build a new telescope. We're going to reuse a telescope. So the telescope that we will use is the Swedish ESO submillimetre telescope, and there's a picture of it. And this is a 15-meter dish, and it was operated at La Silla in Chile from 1987 to 2003, whereupon it was decommissioned. So CEST will be dismantled. It'll be shipped to France for repair and refurbishment, and then it'll be shipped to Namibia. And the University of Namibia has committed engineering staff to help with the repair and the commissioning. So when I mention the overall cost of this project, you've got to bear in mind that a significant part of the cost of any project is salaries of people working on it. So UNAM has made a contribution which translates to about €3.5 million of people to work on this project. So the current plan is that the telescope will see first light in 2024, April of 2024, so only just under 2 years away. Now, as you can see, as you may remember from the picture I showed you with the precarious road up to the top of the mountain, the site has to be developed. So the current state of the top of Mount Gamsberg is similar to what La Silla would have looked like before ESO started developing their telescopes there, or Paranal, where the VLT is, or even Mauna Kea in Hawaii, which is now a major observatory. And yet, if you go back 50 years, there weren't any telescopes there. So Mount Gamsberg, I feel, it could become one of the best observing sites in the world, but of course it has to be developed. And one of the issues is access to the top of the mountain because of this precarious road. Now, through an interesting quirk, the plateau at the top of the mountain is actually owned by the Max Planck Society. Now, I don't really think it's owned. It's probably on a long-term lease. I can't imagine the Namibian government actually selling something like that to a scientific society in Germany. So I suspect it's more of a long-term lease than an actual purchase, actual ownership. And that was done in the 1980s because the Max Planck Society planned to put one of the telescopes, which ended up in Chile, on Mount Gamsberg. Now, the land that leads to the mountain is private, so there's actually no way to get to the mountain without traversing private land. So obviously, we have to sign various agreements with the farm, the farms around the road that leads up to the top of the mountain. And most of those farms are actually game farms. And so, of course, they're very concerned about the impact that lots of heavy traffic taking bits of telescopes up to the top of the mountain would have on their animals. So we have been negotiating with them over the last 18 months to make them comfortable with what we are planning to do. And there were all kinds of rumors going around in Namibia, which, like Botswana, is a small community, saying that we were going to have, I don't know, 100,000 Chinese workers turn up and ruin everything. And that's not the case. The largest part of CEST are 5 metric tons. So the road needs to be improved to take such large pieces up to the top of the mountain. There are alternatives, but really they're not feasible to talk about a couple of them. Cable car, this is used in some of the high observatories in the French Alps, or even airlifting with a helicopter. The problem with that is you're already at 2 kilometers altitude. The top of the mountain is at 2,400 meter altitude and the base at 1,800 meters. So there aren't many helicopters that can lift heavy things at those kind of altitudes, but it is possible. But even though improving the road is a major undertaking, it really is the most feasible. And it'll require a lot of money to do it. So of course, not only do we need to raise the money, we're talking about for the entire project, including the cost of the telescope, the cost of developing the site, and paying the staff to work on it. We're talking about a budget of about 20 million euros. As I already mentioned, the University of Namibia has committed staff to work on it, which equates to about 3.5 million euros. But most of the money still needs to be raised. And this is where I'm hoping Botswana might be able to come into it, not contributing the money itself, but helping raise the money. So let me conclude, and then I would obviously be happy to answer questions. The Africa Millimetre Telescope is going to add to the resolution of the Event Horizon Telescope. We have been able to make a very strong case that it will improve the operation of the telescope. We're going to use a telescope which already exists, which obviously reduces costs, and it's going to be located on Mount Gamsberg, southwest of Windhoek. UNAM is going to be a major partner in the project, and one of the attractions for the University of Namibia to commit people to this project is that when it is not being used for Event Horizon Telescope work, UNAM will be the lead institute to do single dish science. So when it's not being used as a part of a network, you can still do science just as a single dish. And obviously the University of Namibia is interested in having that amount of observing time. So doing that will greatly enhance the research profile and output of the physics department at the University of Namibia. So we successfully completed a preliminary design review in 2019. And the plan is that the telescope will see first light in April of 2024. So that's it. Let me finish there. And I'm going to stop my screen sharing just for a minute, turn my camera back on, then go back to screen sharing. So obviously I would be happy to answer any questions that people may have. Do you want me to come out of screen sharing? I can see, oh yes, something else is on my screen now. So let me come out of screen sharing. I will stop my own screen sharing.
That was very informative, Rhodri. Thank you for that. I'm sure there would be questions from the participants. We have almost 40 participants. There was a question that came to my mind, Rhodri, when you were showing that slide earlier on in your presentation of the center of Sagittarius, showing X-ray emissions. And I was wondering, how is that emissions from the black hole of our galaxy? Could you explain that, please?
Oh, okay. So remember, the definition of a black hole is that the object is too dense for even light to escape. So any emission that you see from a black hole is actually not coming from the black hole itself. It's coming from outside of the event horizon. And what our understanding of black holes is that you have this incredibly dense, massive object, which then, of course, draws in material from nearby. And so what you have around most black holes, and we expect that the supermassive black hole at the center of Milky Way galaxy is the same, is you have what's known as an accretion disk. So you have a disk of material which is falling into the black hole, and that material becomes incredibly hot through friction, and that's why you see emissions at X-rays. So the X-ray emission of the accretion disk around black holes is basically thermal emission of gas, which is at millions of Kelvin.
Okay. There is a question on chat. Is it really possible to find a good image of Sagittarius A with the AMT, like the one obtained by EHT?
Well, no, because the AMT hasn't been built yet. So remember that in order to get these images of the central black hole, you use these millimeter wave dishes in a network. So even the observations of Sagittarius A star that led to its discovery in 1974 were using a network of telescopes, the Very Large Array in New Mexico. Now, that's a network that only covers a few kilometers. So on its own, the AMT, or really any of these telescopes in the EHT network on their own, would not be able to image the event horizon of the black hole because the size is just too small. But working together, they can use interferometry to improve the resolution. So one of my slides illustrated the improvement that we would expect in the resolution by having the AMT as part of the network. So, some people might think, oh, well, hang on, the EHT has done this work. They released the images in May. It's already been done. So where's the justification for a telescope to add to the network? But of course, those of us who work in science know that once you have your first observation of something, you can often make the case, a stronger case, to improve the experiment by adding something else. That the first observation shows that it can be done, and then of course you can very often get more funding to work on a better version of the experiment, which is what the AMT would do by adding to the network. It would give you better results than we've already been able to obtain.
There's another question. I'm interested in the theoretical implications of the EHT observations. There are bright blobs of plasma observed on Sagittarius A in a zone considered to be the photon sphere. This observation is not accommodated in GR because no stable matter orbits are expected below the innermost stable circular orbits. Doesn't this raise a contradiction in GR?
Okay, right. That is quite a detailed question, and it would actually be quite difficult to answer. But what I can say is, because the person who put this question has mentioned GR, general relativity, it's certainly the case that as we get better and better observations of these supermassive black holes, at the moment we've got an observation over a period of a couple of weeks of Messier 87's supermassive black hole. We've now got these observations of our own galaxy's supermassive black hole. It's certainly the case that as we obtain more observations with the existing network, and then hopefully with an improved network in a few times, it'll help us test certain aspects of general relativity. So it may be that we do find some flaws in general relativity when we actually make observations which are detailed enough to be able to test specific aspects of general relativity. I remember reading a book in the mid-1990s, I think, which was all about the various tests which have been done of general relativity. But most theories break down, or at least show their limitations, when you put them in more extreme situations. And certainly the environment around a supermassive black hole is probably the most extreme environment that we are able to study. And therefore, if there are flaws in general relativity, if there are weaknesses in general relativity, that is the best place to look, because that's the most likely place to find weaknesses. So it may be that in 10 years' time, we're saying, oh yes, the EHT helped show that there were some limitations or flaws in general relativity. It's too early to say what the observations show at the moment, because we're just at the beginning.
Is there a question from Mr. Marongwe? Question, Rhodri. It says, what is your role in this project, and also how many people approximately would be working on this project across the world?
Okay, so let me differentiate between the two projects. There's the Africa Millimetre Telescope, and then there's the Event Horizon Telescope. The Event Horizon Telescope has more than a dozen dishes in it, and there are literally hundreds and hundreds of people working in the Event Horizon Telescope project. Come into the Africa Millimetre Telescope project, the telescope that's going to be built in Namibia. That's a much smaller part of the larger project. And until I left University of Namibia a couple of months ago, sorry, not a couple of years, a couple of months ago, I was the project scientist for the Namibian side of the project. So the project, the Africa Millimetre Telescope project, is being headed up by Radboud University in the Netherlands. And the University of Namibia is a junior partner in the project, and I was the Namibian project scientist on it. Now that I've left UNAM, I no longer have that position, but I am hoping that Botswana, through my position now at BIOST, can become involved in this project for several reasons. Obviously, it would be good for BIOST and Botswana to be involved in such an interesting project, but from the project's point of view, they are actually keen to have another Southern African country involved because it'll help raise funds. If you're applying, for example, for European funding, and you've got two African countries as part of the project rather than one, it increases your chances of getting funding because there is money in EU funding, but also UK funding to help develop scientific infrastructure in developing countries. So yeah, my hope is that over the next year or so, through BIOST, we can sign a formal agreement with the project, and then quite what I'll be given when I'm officially back on the project, I don't know.
That would be wonderful. There's another question. What's the connection between the SKA and the AMT, or is there a connection?
Yeah, well, there is a very important connection, and that is they're basically using the same idea of very long baseline interferometry. So the SKA works on the idea of linking telescopes in Southern Africa together to produce these incredibly detailed images, and that's exactly what the EHT, the Event Horizon Telescope, is doing. So it's the same ideas behind it, it's the same technology. So there's a crossover in terms of the expertise that you need to do either project, and so my hope is, and this is what brought me to Southern Africa 5 years ago. I firmly believe that Southern Africa is going to become the hotbed of radio interferometry astronomy over the next 20-30 years, and the AMT will hopefully be part of that. The SKA is obviously going to be the major observatory in the world when it goes into operation. So the technique is the same.
There's another question. What determines the size of the depression observed in the EHT images of Sagittarius A and M87?
Okay, let me bring up my slide because I'm not entirely sure what is meant by the depression. So let me bring up the image, and then maybe the person who sent that question can explain. I think what they're talking about, and correct me if I'm wrong, is they're talking about the sort of slightly brighter and slightly fainter spots in this ring. The hole in the center is the black hole. So that's, at least that's what we believe. Whereas this is the accretion disk, if you like, around the black hole. Now, why there are spots that are brighter and fainter, it's presumably due to different densities of gas. I don't know the details, and people are probably working on understanding what that's telling us. What we do know, if I go back to this slide, and let me just go into presentation mode. So so you can see with the images that we obtained of Messier 87 that there is a very slight, subtle, but there is a definite change in the appearance of the donut, if you want to call it that, over the course of a week or so. So these changes are things that we need to understand the details of. So, we've got, for the first time ever, we have not only observations of the material accreting into a supermassive black hole, but they're detailed enough that we can actually see differences in the brightness and therefore presumably temperature and density of the gas in different parts of the ring around the black hole, and understanding what that has been caused about is the next challenge.
There's one more question. You may have to repeat yourself here. Why is there an accretion disk?
Okay, so the accretion disk is basically, so between the stars, you have what is known as the interstellar medium. So space is filled with gas and dust. And so the accretion disk is basically due to the intense gravity of the black hole. The material that's in the interstellar medium gets drawn into the black hole, and as it moves closer to the black hole, it basically forms a disk around the black hole, in the same way that when you have any gas that is rotating fast enough, it flattens out into a disk. So we've observed these accretion disks around local black holes of the end product of massive stars, and now we're seeing them around the two supermassive black holes at the center of two galaxies. So it's material that is drawn into the gravitational influence, if you like, of the black hole, and then it swirls into the black hole.
Good. Thank you very much, Rhodri. We'll be having a recording of this posted on our website, the Astronomical Society of Botswana website.
Okay.
Thank you very much once more, Rhodri, for this informative and very, very interesting presentation.
You're welcome. It was my pleasure.
Look forward to hearing more news on progress in Namibia.
You should get me back now in 18 months when we're hopefully just about to start observing with the telescope, and hopefully I'll have good news.
Very, very exciting.
Okay. Thank you very much.
As the months roll on. Thank you so much, and good evening to everybody else. Thank you for joining us.
Thank you. Thank you.